Hello. So let's do another example. And so we're going to show that, so this is an example for which the base case does not exist. So what we're going to do is we're going to attempt to prove that for all natural numbers n squared plus 7n plus 1 is even. And so what we're going to do is we're going to skip the base case for now. And then we're going to write down the inductive hypothesis and then try to do the induction step. And the induction step is going to actually work. But then we'll see, we'll go back and circle back to the base cases and see that the base case, there are no base cases. No number that we plug into this is ever going to be even. And so let's do that. So let's do the inductive hypothesis. So assume that P of K is true for some K greater than or equal to 0, i.e. assume that K squared plus 7K plus 1 is even. So another way to write that is equal to 2 times L for some integer L for some K greater than or equal to 0. Great. And then just like in all the previous examples, we're going to say consider K plus 1. And so what we want is we want K plus 1 squared plus 7 times K plus 1 plus 1. We want this to be even, and so we want this to be equal to ... 2 times something, 2 times some integer. And what we're going to see is that this does, in fact, actually work. And so let's do that. So we're just going to kind of multiply this out. So if we FOIL out this K plus 1 squared, this is going to be K squared plus 2K plus 1. So that was K squared plus 2K plus 1. That's the K plus 1 squared. And then 7 times K plus 1, that's 7K plus 7. So we're going to do plus 7K plus 7. And then we still have this 1 over here. So plus 1. And then we want to use our inductive hypothesis. And so our inductive hypothesis is this K squared plus 7K plus 1 is 2 times L. So we want to identify K squared plus 7K plus 1. So let me kind of mark that K squared, 7K, and then 1. And so let's write that down. So this whole sum is going to be K squared plus 7K plus 1, and then plus everything left over. So everything left over is 2K plus 1 plus 7, so 2K plus 8. Okay. And then we can use our inductive hypothesis. So K squared plus 7K plus 1, that's equal to 2 times L for some integer L. So this is equal to 2 times L. That's weird looking now. 2 times L plus, and then similarly, this we can factor out a 2. This 2K plus 8 is going to be 2 times K plus 4. And so this is going to be plus 2 times K plus 4. And then now hopefully you see where I'm going. So each of these terms has a 2 in it, and so we can factor it out. So we can factor out the 2, and we have 2 times L plus K plus 4. And so then we see that in fact, the predicate is true for the K plus first term. So K plus 1 squared plus 7 times K plus 1 plus 1 will also be even as long as the previous term is even. But as I mentioned, this function up here will never be even. And so let's plug in some numbers and actually see that. So for n is equal to 0, if we plug in 0 squared plus 7 times 0 plus 1, that's going to be 1, which is not even. And then if we do n is equal to 1, that's going to be 1 squared plus 7 times 1 plus 1. So that's 7 plus 2, which is going to be 9, which is also not even. And let me kind of explain to you why it will never be even. So when, and here, let's actually kind of rewrite this a little bit and we'll see why. So if I factor out an n, this is going to be, well, a factor out an n from these first two terms. This is going to be n times n plus 7 plus 1. And so now if we think if n is even, then an even number plus an odd number is going to be odd. And so then this, so if n is even, then this number over here is going to be an odd number. And an even number times an odd number is going to be even, plus 1 is going to make it odd. So when n is even, this is going to be odd. Now let's do the same thing when n is odd. When n is odd, two odd numbers added together is going to be an even number. So when n is odd, this is even. So again, this product is going to be even. When we add 1, it's going to be odd. So in either case, whenever n is odd or n is even, this function up here is odd. And so this is a really interesting example, I think so at least, that it's really useful and really important that when you're doing proofs by induction, you do examples and you don't, the examples and the base cases are super important.